And last time, if you remember, so I taught you Solaris scheduling, how normally scheduling takes place at Solaris operating system. Okay, so you know already about this. So I would like to go ahead and we'll start algorithm evaluation. Okay, so okay. So how to select CPU scheduling algorithm for an OS. So OS means operating system. How one should select a CPU scheduling algorithm for an OS. This is what we will study, what I will teach you today in the remaining slides. Determine criteria. For that, we have to determine the criteria, then evaluate algorithms. Yes, first to determine the criteria and then to evaluate the algorithms. Deterministic modeling. Okay, so what is deterministic modeling? I mean, if you want to determine the criteria, so for that you need to use any deterministic model. Okay, type of analytic evaluation. There are two types of evaluation. The first one is analytic evaluation, which normally takes a particular predetermined workload and defines the performance of each algorithm for that workload. Yes, in analytic evaluation, what normally happens, the predetermined workload is taken or considered, and then the performance for each algorithm is defined for that workload. Okay, let's suppose consider we have 5 processes arriving at time at time 0. Okay, but what does it mean that let's suppose P1 process 1, its burst time or its execution time is 10 millisecond or nanosecond, whatever the unit is, or whatever the normally you consider the unit. So then P2, its burst time is 29, then P3 burst time 3, and then process 4, its burst time is 7, and then process 5, its burst time is 12. So how now keeping in mind the following processes, one may need to determine the how should I say, determine its overall evaluation, how much time it takes and how it got executed, which algorithm is taken normally are considered. Okay, so let's go to the next slide, then you will understand. Please stay with me. But before going to the next slide, uh, I would like to check the comment section of this group, if there is any student. Okay, we have students and more students are coming soon. They will join us. So uh, for each algorithm, calculate minimum. In deterministic evaluation, what we normally do for each algorithm, we calculate minimum average waiting time. Okay, average waiting time. I'm using the word average. Okay, minimum. Simple and fast. So deterministic evaluation, it is simple and fast but requires exact numbers for input. Applies only to those inputs. Yeah, what does it mean? Okay, we have, let's suppose, 5 processes here, and the burst time for each process is defined here, are declared here. So process 1, its execution time, or the time it takes to execute this process. Mind you that process, task, job, all these things are the same thing. When a job or task is in progress or it is in execution, then we call it process. Okay, so P1, its execution time is 10. The execution time of P2 is 29. The execution time of P3 is 3, the smallest job, okay, or the shortest job. And then the execution time of P4, process 4, is 7, and then the execution time of P5 is 12. So we have 3 algorithms to determine which algorithm is more, how to say, analytic, which algorithm is simple and it can be opted or it can be chosen. So this is what I taught you here in this slide. We need to determine the criteria, then evaluate the algorithm, and how we may choose a CPU schedule algorithm for an operating system. So this is the procedure. We have three algorithms here. The first algorithm is first come first serve, or FCS, and then we have non-preemptive shortest job first, SJF, shortest job first, or we may also write it shortest first job, and then RR, round robin. But let me remind you, FCS, which uses the concept of first come first serve. We already studied FCS, but I just want to uh, remind you, or I just want to help you to this. Here we have FCS or CF is completely fair scheduler, and it uses the concept of first come first serve along. I think it's not. I think we already studied. It's a mix of a few different algorithms or policies. So this is CF is completely fair scheduler. Okay, so completely fair scheduler. Okay, so we have P1 is 10 milliseconds. So you see here, from 0 to 10 millisecond, P1 this job got executed. And then we have 29, so 10 plus 29 until 39. So from 10 to 39, the P2 process, this was it was executed. And then P3, it is only 3 milliseconds, so 39 plus 3, 42. So from 39 to 42, P3 got executed. And then from 42 to 49, we added 7 and 42. Here is the 7. P4 process 4 is executed. And then P5, 12. From 49 to 61. P5, this process was executed. So this is how in completely fair schedule FCS, the you see the completely fair scheduler. Okay, the completely fair scheduler, CFS, completely fair scheduler. So it was considered that it is completely fair scheduler. So, and completely fair scheduler, or fair complete scheduler. So it's normally the 28 milliseconds. So here its maximum time to execute a job is 28 milliseconds. But here in so it was about completely fair scheduler, or fair completely scheduler, and now we have shortest job first. So in non-preemptive shortest job first, we have a quantum maximum time allowed to execute a job or process is 13 milliseconds. So here we have first job 10. So from 0 to 10, P1 is executed within the time quantum, or within the time slice normally given to a processor to execute any particular task or process. And then the P2 is 29. So the 20, yes, 29. But we have the maximum time to execute a job is 13 milliseconds, and here it is 29 milliseconds. So this is shortest job first. So first of all, the shortest job, which is 3 milliseconds, is executed. Then P4 7, which is the second shortest job, then P4 is executed, and both of them are executed within the time slot, as the time slot is 13 milliseconds, so they don't require extra time. And then you see P1 is the third shortest job, so P1 is also executed within the time slice, which is 13 milliseconds. And then P5 is the fourth shortest job, 12, so it is also executed within the specified or defined time slice, which is 13 millisecond, and 12 millisecond is less than 13 millisecond. So next is the largest biggest task, which is 29. So then from 32, if you will add 29 and 32, so it becomes 61. So then the largest or biggest job, which is P2. P2 is executed at the end of all, or at the end of very last. So I mean, in the very last, it is executed the P2 job. So it was shortest job first, and then we have another algorithm, round robin RR. So P1 again 10, then P2 29. So you see, P2 from 10 to 20, it got executed, but after that it was preempted, and P2 came again here, you see, and then came again, because P2 is the largest job and it needs 3 rounds, 3 processor rounds to get completed its execution. So that is why in round robin we normally preempt a job. Preempt means we normally take a job from the processor and then we allot another job to the processor, and when the turn of the preempted job comes again, then the processor get executed again, and if that job gets executed get executes in the specified time slice, so okay, it got finished. If not, then again it comes in its third turn, and the processor again gives its attention or time to that process again, and if again that it was not executed, it will have another turn again, and that is why it is called round robin. So you see the same concept, P1 P2, and in round robin first P1, as it is small, then P2 will come again, you see, second and third time, as it is a biggest process, it takes almost 29 milliseconds to get execute. Okay, then P4, and then P4 is smallest, so it needs only one time, it needs the processor only once time to finish itself. And then P5, okay, P5 needs to will turn will also come in second turn. You may see here a very short time, I mean a very short processor time taken to get itself finished, and then P2 again. So this is the deterministic evaluation. Now we know which algorithm is best for us. So you guys have almost covered this course with me, and I hope now you can judge which algorithm is best, so as far as deterministic evaluation is concerned. Okay, so this is normally how the deterministic evaluation takes place. You normally consider 3 or 4 algorithms, and then you see which algorithm is analytic and which algorithm needs to be chosen for scheduling, CPU scheduling within an operating system. Okay, let's go to the next slide. We have queuing models, and queuing models, we describes the arrival of processes and CPU and IO burst probabilistically. Okay, in queuing models, we normally describe the arrival of a process when the process got arrived, and then the CPU and IO burst probabilistically. Yeah, the CPU or IO burst. Normally, the IO burst means the time a process takes to use input output devices, or to use IO devices. Okay, commonly exponential and described by mean. Yeah, uh, it means that such determinism or calculation is in exponent, or these are exponential and described by mean. By means average. Normally you can't one can't explain it in, how to say, in a perfect way, in accurate figures. We always try to explain it in terms of mean or in terms of average. Computes average throughput. You see, the word average is used. The average throughput means the number of job or tasks performed in unit time, utilization, waiting time, etc. And then in queuing models, the second point is computer system described as network of server, each with queue of waiting processes. Yes, computer system described as network of server. Yeah, we have a network of servers. We have a lot of servers connected in a network, and this is how normally a computer system is explained or defined or described, each with queue of waiting processes. And in each system there are many queues or different queues, multi-level feedback queue. We all have already studied this algorithm in which normally 2 or 3 queues take place and so this is how, I mean, in queuing models we may have different queues for processes in which they are waiting. Okay, so knowing arrival rates and service rates. Okay, arrival rates means when a process arrived for the processor and how much time it took to get serviced. I mean, how much time the processor took in executing that process. So service rates. Okay, and then computes utilization. And in QE models, we compute the utilization, how much an algorithm or a task or a process is got utilized. Average queue length, and what is the average queue length? How many processes can be accommodated in a specific queue? Average wait time, and what is the average wait time? Wait time means when the process is in wait to get the CPU, to get the processor to be executed. So we normally call it average waiting time. You know, there are a process can be in different status, like ready status and waiting status, active status. Okay, so there are different statuses. So let's go to the next slide. I hope you understood this slide, but before teaching you this slide, I would like to go to the comment section to see any question from the students. Okay, here now I'm in the comment section, and some students are greeting me. Eid Mubarak, they are saying Salam Walaikum Salam, Eid Mubarak to you guys too. And Bashir, okay, so let me drink water. I will be right back after a couple of seconds. Okay, tell him that I'm coming to settle the score with him. Okay, I'm busy in my class. We'll talk later. You may go now. I said go. We will talk later. So kids are always naughty. One of my kid, he had a complaint. So okay, let's go back to he was my nephew, in fact, but still he is my kid, a family member. Okay, so we were here. Jhon Little's formula. There was a person, his name was Jhon Little, and he introduced a formula for what? I mean, it is a part of queuing models. Okay, so N means average queue length, W average waiting time in queue, how much time a process takes to wait for the processor. This is what average waiting time means. Average queue length, and how many processes can be accommodated in a queue or can be put in a queue. So this is what we call it normally N. And average arrival rate in queue. Okay, you know, service rate and arrival rate, there is a difference. Arrival rate means per unit time how many processes gets entered into the queue and how many processes are going out of that queue. So normally we call it arrival rate and departure rate. Okay, so we normally represent it or them with lambda. Lambda is a Greek symbol and you people are familiar with it. So how Jhon Little is explaining his formula. He says that in steady state, processes leaving queue must equal processing arrival or arriving. Okay, he says that the rate at which normally processes leaves the queue is equal to the rate of the processes with which they are entering the queue. Yes, this is true. He's saying right. I hope you are understanding. Let me explain it for you guys in Urdu as well. वो कह रहा है कि जो प्रोसेसेस की क्यू है, क्यू आप जानते हैं एक डेटा स्ट्रक्चर है, जिस रफ्तार से उसमें प्रोसेसेस आ रहे हैं प्रोसेसर तक जाने के लिए, तो कहते हैं वो रफ्तार और जिस रफ्तार से उस क्यू से प्रोसेसेस निकल रहे हैं दोनों बराबर है. अगर बराबर नहीं होंगे तो इट विल बी सीरियस प्रॉब्लम देन. हाउ? Because okay, let's suppose that the entering rate is fast and the departing or going out rate is slow. So what will happen after a couple of seconds? A huge amount of processes or too many processes will take the shape of a dump inside that queue. There will be a lot of processes, and then those processes will get stuck there in that queue as the living rate, I mean, the process living rate is very slow, so it may become a problem. So this is here, John Little, he's saying right. And then what he says, valid for any scheduling algorithm and arrival distribution. Yeah, he says that this is valid, this is true for any scheduling algorithm and for any arrival distribution. I mean, arrival distribution, at what rate normally the processes needs to be arrived in the queue, okay? And you know, in the processor they have some attached queues, and they normally the processor uses those queues to perform the system in an accurate way, okay? Let's suppose, for example, if on average 7 processes arrive per second, okay, in 1 second normally 7 processes get entered into the queue, and normally 14 processes in queue, then average wait time per process is 2 seconds. Yeah, 7 processes are arriving per second, and normally 14 processes in the queue, and there are 14 processes in the queue, so the average wait time per process will be 2 seconds. I hope you are understanding what does this 2 second mean. I'm repeating, okay, I'm repeating, but let me clear my glasses with a silky cloth, as I'm not seeing okay properly. Okay, let's. So I mean, if there are 7 processes getting into the queue, and there are totally 14 processes, so the average wait time per, so each process will have to wait 2 seconds, and after 2 seconds it will get the CPU to be get executed by the processor. So this is what it means. So let's go to the next slide. Simulations is a new topic, and I mean, it is almost attached to, or it is how to say, a connected topic with the queuing models and deterministic evaluation. But before teaching you this, lads, I would like to go to the comment section to see any question from any student. Okay, no question. Okay, so queuing models limited, it means that the queuing models are limited, and there are some issues in the queuing model. So there is a new method, simulation. So using the simulation method is normally preferred. Simulations more accurate. Yeah, simulations are accurate and queuing models are not accurate. Why? As I already said, that you need to talk in terms of average or mean computation. Okay, you can't one can't tell the accurate exact figures of computation in queuing models. So here in simulations we might get the accurate computation, okay, more accurate than queuing models. Program model of computer system and programmed model of computer system, clock is a variable. Yeah, in simulations we have a programmed model of computer system. I mean, simulation is a program means program. Normally the user or the programmer sets it, and it gives the overall model or design of the computer system, in which you may see the scheduling algorithms, and from which you can calculate different things or different statistics. Okay, here in simulation the clock is variable, gather statistics indicating algorithm performance. Yeah, in simulation we gather statistics, different statistics, which indicates the algorithm performance. Data to drive simulation gathered. What does it mean? Data to drive simulation gathered, I means the data which normally user or the programmer puts or enters into the system, into the simulation, and it shows the overall drive, it shows the overall performance, how the simulation works. This is what it means. Random number generator according to the probabilities. Yeah, if you want to check a system, you need to generate random numbers, and you need to check the system or the model with different parameters, so that you can get different probabilistic results. Okay, distributions defined mathematically, and yeah, Distributions defined mathematically or empirically by means of observations or experience rather than theory or pure logic. Yeah, I mean, you can't talk in theory. You need to, by means of observations or experience rather than theory or pure logic. Yeah, I mean, empirically means to explain something after observing it, after first observing it, after first experiencing it. Okay, so this is what it means, and uh, uh, you may also present the distributions using mathematical notations. Trace steps, record sequences. What is trace steps? Coming on the next slide. Trace steps record sequences of real events in real system. In the real system, normally if one needs to record the sequences of real events, so they may use trace steps. Let's go to the next slide. Trace steps. Okay. So here are the trace steps. What is here given on this slide? We can understand it from its title, evaluation or heading, main heading, evaluation of CPU schedulers by simulations. Yeah, here we are having three different schedulers. Our algorithms, FCFS, first come first serve, then shortest job first, and then RR, round robin, with its Q quantum is equal to 14. And using the simulation, we are evaluating them, and here are the trace steps. These are the trace steps. 10 milliseconds normally taken by the CPU, and then 213. Sorry, this is the trace steps, not the milliseconds. And then 213 is another trace step for this IO input output, and then again CPU 12, and then again IO 112, then again CPU 2. These are the trace steps, and this is the actual process in execution. Okay, a process which is in execution, and it's and dispatcher, it context switches. I mean, context switching, it switches the process again and again, sometimes towards the IO, and sometimes then the process is then brought back towards the processor to be get executed, and then IO deadlock, execution, blah blah blah. All these things happens, and all these things are traced with their indices are traps. So okay, so this is, you can understand easily, simulation of first come first serve, then simulation of shortest job first, and then simulation of round robin. The round robin is an algorithm, and I also gave these algorithms to you guys, if you remember, in your assignment, and you already know a lot of things about these algorithms. So this is how we normally we can simulate different algorithms to evaluate them and to give the accurate statistics. So simulation is the best way to analyze or to observe the performance of your algorithms. It is better method than queuing models. Okay, I hope you are understanding what I'm saying. Let's go to the 67th slide. We have almost 68 slides, so this is the last one slide, as we are having thank you on the next slide. Okay, so please stay with me. I'm keen to go to the comment section if we have any questions from students. No question. Okay, so implementation, even simulations have limited accuracy. Yeah, what does it mean that simulations are also having limited accuracy but better than queuing models? I mean, it's not easy in different fields, in different evaluation. It's not easy to achieve 100% accuracy. You may, okay, if in queuing models you are achieving, let's suppose, 98% accuracy, so by using simulations you may achieve 99% accuracy, but 100%, oh, it's not easy. Yeah, but it also not impossible. It's possible, but still this world is open for research. You may have some further research how to get 100% accuracy of schedulers in operating system. So this is an open research area, and those students who are interested to have research, so they may research on these topics. Okay, just implement new scheduler and test in real system. Yeah, this is what I'm also saying. Just implement some new scheduler and then test them in real system. Real system means in live, in open, in active operating systems. Okay, but it will cost you a high cost. It will take a high cost and high risk. There is a high risk. Okay, different things may happen, particularly you may crash your hardware, deadlocks may come, some of your apps may stop working, and there may some other issue also arise, or some other issues may come in your operating system. Environments vary, yeah, the environments vary, like Linux and Windows, and then Solaris, Ubuntu, and then further flavors differs, then the mode differs, kernel mode, user mode, then the parameters, the environment settings, all these things you need to keep in mind. These things vary, okay? Most flexible schedulers can be modified per site or per system, yeah. The most scheduler and flexible, the most flexible schedulers are algorithm. They can be modified per system to see any improvement, and if you see any improvement, then you may shout openly that, yeah, I got another algorithm which is best than the current or existing algorithms, and then it can be a new research. So this is what I'm telling you guys. You can have some research, you can implement some new scheduler, and you can test them, okay? And then, okay, we have last two bullets or points, or APIs to modify priorities. Yeah, APIs, application programmable interfaces, and you may use APIs to modify the existing priorities of different algorithms to get some new accurate algorithms. This is what you can do. But again, environments vary. Yeah, environments vary. You have to keep in mind the environments which vary, and you have to be cautious, okay, to have your experiments and to get some success. So guys, that's all for today. My next slide, okay, you can see my next slide, end of chapter. So chapter 2 got ended, and we have finished chapter 2, and the chapter 2 is CPU scheduling, and we discussed a lot of POSI schedulers, thread schedulers, and blah blah. We studied a lot of things. There are almost 68 slides in this presentation or in this lecture.